We're back on surfaces as a warm-up. Please try this. Parametrize the surface, which we draw over here. So x-axis, y-axis, z-axis, and the picture I have in mind looks like this. So it's a cone, and we've got here on the y-axis 10, and in fact at the widest the radius here is 10 as well. So there's a lot of ways that you can do this, so don't be too dismayed if your answer looks different. But I'd like to write x of uv, y of uv, z of uv, and I'm going to actually go with y is going to be the variable u. Now, you could have something whose setup is entirely different, but if you have something like I have here and just a single variable v, that's fine. Now u, if it's the same as the y value, also happens to be the radius of the circle, and so perhaps the easiest thing to do is u times cosine of v, and then for z, u times sine of v, and we'll go with u takes on values between 0 and 10, and v takes on values between 0 and 2 pi. So this information here is what gives you what we call the parameter domain. The parameter domain, let's write that better. Okay, that's given by this information. Please note that there are many other possibilities for an answer for this. Okay, well, just important enough that let's just write this down. There's many possibilities. You can just use the app to check if yours is one that works. Though, for better or worse, I'm going to have to come back to this example, this warm-up a little bit later today, using the way that this has been written out. Okay. Let's also just note that we can write this information. We can also write this. This is new, okay, as a vector function. So we'll have something like this, and r of, in the past it would have been just t, but now it's r of u comma v is equal to angle bracket u cosine v comma u sine v. So I know that things maybe look a little strange to write it like this, but it's sort of the same pattern we saw before, where if you had parameterization using just a single variable t, then really how different is a parameterization versus a vector function. And this will be important to be writing down our parameterization information here in now the form of a vector function, where the x formula is the first component, the y formula is the second component, and the z formula is the third component. You'll see very shortly why this is necessary, because let's take a look at the following question. In fact, let's let r of uv be the following vector function, the one that we just looked at. So angle bracket u cosine v comma u sine of v, and let's find the vector function r subscript little u. So we're going to take a partial derivative and then cross product that with vector function r, the partial derivative with respect to v. So let's work out just first just the partial derivatives. So when we take a partial derivative of r with respect to u, we won't write the of uv here. We could do that, but let's just leave that out right now. Okay, we're gonna get angle bracket cosine of v comma 1 comma sine of v. So that's what we get when we differentiate each of the components, each individually, independently, with respect to u. And then if we find the partial derivative of r with respect to v, we're going to get negative u sine of v, comma 0, comma u cosine of v. Now let's take the cross product of these two vectors that we just found here and there. So ru cross rv, very important calculation today, very relevant to the things we're doing. So standard cross product formula here, right? Determinant, first row ijk. Second row will be the entries of this r sub u vector. So we'll have cosine of v, 1 sine of v, and here we'll have negative u sine of v, 0 u cosine of v. So if we compute, we'll have I times u times u cos times based on, sorry about that, based on the 2 by 2 determinant here, 1 times u cosine v, okay, so that's just u cosine v, minus 0 times whatever, so let's not do that, minus j times, so it'll be this times this minus this times that. But if we think about it here, there's cosine u times cosine squared v plus u times sine squared v. So if we factor out the u, use a trig identity, we're just going to be left with just a u in here. Okay, so this, this is after applying a trig identity. I just don't want to write out too much work here, followed by the vector k times u sine v. So if we, let's see. So if we clean this up in angle bracket notation, we'll have angle bracket u cosine v, comma negative u, comma u sine v. Now, what I'd like to do, we're done with that question, but I'd like to consider, just generally speaking, consider S to be a parametrized surface. You just have some surface that's been parametrized. And so we think of a surface as living somewhere in three-dimensional space. So I've just drawn some axes out somewhere. But the point is there's this surface here. Okay, we just, some two-dimensional like creature. It's like a towel has just been rippled in the windy air, and then you just take a picture of it. Okay, and then what we'll do is, like at a specific point inside this picture, there's just based on the rippliness of the towel, there's a little patch here. If you just travel a little bit in the u direction and a little bit in the v direction. What I mean by that is, so this might be a bit ripply here. Okay, let's try this again. Yeah, let's try drawing this a little cleaner. Okay, so based on that one sort of base point here, you might have something that looks like this, and where would it have come from? Well, in the parameter domain, so in uv, you'd have like this point, this thick drawn point would be this point, and here you just really have a du dv. Like this is a little rectangle with the specific ith intervals u value called u sub I star, and the specific jth intervals v value called v sub j star. And then if you run through all the values of u and v in that tiny little rectangle, it ends up being these points here inside the surface. So let's try to annotate and talk about what's really going on here. Is at the point x of u comma v, comma y of u comma v, comma z of u comma v, a little piece of the surface is approximated by actually the area of a parallelogram. So here, if you just looked at the velocity vector this way and the velocity vector this way, it would create the shape of a parallelogram here. Okay, area of a parallelogram. And the area of that parallelogram can be computed directly. So we write this as a delta capital S. And what it actually ends up being is it's going to be the magnitude of the cross product we just computed. So R sub U cross R sub V finally times a delta U, delta V, where the delta U, delta V are right there in the picture. Delta U, and this distance is delta V. We won't go through all of why that really works out, but it really just has something to do with a property of cross products. So taking the cross product of two vectors ends up creating, and then looking at the magnitude ends up creating the area of a certain parallelogram. We're just going to go with that, and we'll take a look at the following then definition. If S is parametrized by R of u comma v equals x of u comma v comma y of u, comma v, comma z of u, comma v. So we have a parameterization using two parametric variables, or two parameters u and v, just written instead as in the form of a vector function with the property that u comma v should belong to D, and so this D is the parameter domain. Then the surface area. I don't really think this should be called a definition. It's really more of a theorem, but we'll just go with it. Okay, the surface area is, well, given this way. So the area of this surface S, okay, is actually going to be found as the double integral over D, so over the parameter domain, of this, we're really just taking what's right over there. It's the magnitude of the cross product of these partial derivative vectors. And then dA, where this dA is going to either be du dv, or if it's more convenient, dv du, and that's just meant to copy the delta u delta v that was right there. Okay, so this nice little formula will be super useful for us. In fact, let's go ahead and do a quick example of this. So let's, as a question, find the surface area of the cone from the warm-up. So for the first question of the day, the warm-up was to find the area of a cone, was to just parameterize a cone, and now by finding the surface area of that cone, we're just finding out how much paint we would need to buy in order to paint the entire cone. So, to formulate an answer to this, let's just recall that the parameter domain that we had was u went from 0 to 10, v went from 0 to 2 pi. We had already computed r sub u cross r sub v. In fact, we can just go take it from above. Let's just do that. It was right here. Okay, u cosine v, negative u sine v. Just place that right there, and then we can then compute. Okay, so we've got almost all the pieces. Let's just now actually compute the magnitude. So just we're taking maybe a couple more steps than you might in the future. You might feel comfortable skipping steps later, but let's just take the vector that we had just computed here and compute its magnitude. Okay, so we'll have here root. We need the sum of the squares of the components. So u cosine v quantity squared plus negative u quantity squared plus u sine v quantity squared. Now, if you work out u cosine v squared plus u sine v squared, isn't that a cosine v squared plus sine? Yeah, cosine squared v plus sine squared v. Once you factor out a u squared, so there'll be a u squared there. There's also a u squared there. The negative ends up squaring away, so we end up with root 2u squared. Root 2u squared, and while the square root of u squared should be the absolute value of u, because u is always positive here, this works out that we could just write u times root 2. Okay, so then the area, we're just now going to set up what's going on here. The area should be the double integral over the parameter domain of this u root 2 and then dA. But now we've got to convert that dA into a du dv integral or a dv du integral. Now, since our parameter domain actually creates the shape of a filled-in rectangle, we'll just stick with rectangular coordinates here. Yeah, so let's just have u root 2, and then the dA, let's just turn that into a du dv. Du dv, with the u integral being on the inside, that inner integral should be from 0 to 10, and then v on the outside, the outer integral should be from 0 to 2 pi. Give this integral to yourself back when we were looking at the previous chapter, and maybe the u's and v's look bothersome, but just switch all the u's to x's or whatever. U and v are just the names of new variables, and if you work out all the details here, you should end up with the surface area being 100 times pi times root 2.